AB Calculus, Section 4.5, Differentials and Approximations. This is day 1 of 4.5. We'll continue with more approximation work in day 2. Objectives for this lesson are to understand the difference between a derivative and differentials, approximate a function using differentials, and approximate error by using differentials. Okay, so before I get into this statement here, let's take a function, let's call this function f of x, and let's take the function on an interval from a to b. Okay, that would yield for us values f of a and, approximately speaking, f of b. Okay, so dy and dx are called differentials. The differential dx represents the change in x of both a tangent line and the curve. So let's highlight this. The change in x from a to b, right, this distance from here to here, we call dx. Okay, we actually also call that delta x. We'll talk about the difference here in a minute. Okay, so the change in y of the actual function, okay, we call this delta y. All right, now let's continue with the statement. The differential dy represents the change in y along the tangent line only. Okay, so what tangent line are we even talking about? Well, if I drew a tangent line to f of x at x equals a, it would look kind of like this. Okay, there's my tangent line. Now that tangent line is built by a change in x and a change in y. Okay, so dy is the change in y according to the tangent line. All right, and dx is this length, which is equivalent to delta x. Now, if you look at the difference between delta y and dy, what we're left with is a difference represented by this distance. Okay, this would be considered the error. That would be the error. That would be, right there, would be delta y minus dy. Okay, so I'm going to put absolute values around that because in some cases, if f of x is concave down, dy might be an overestimate of delta y. Okay, so let's talk just some details here. Well, f of b, right, f of b should equal f of a plus delta y. All right, that's pretty clear. Now, how can I approximate delta y? Well, f of b would be approximately equal to f of a, which should be known, plus dy. Okay, so we're going to come up with some methods. I want you to just kind of keep this in your back pocket right here. We're going to come up with some methods on how to find, actually one specific method on how to find dy, which is, again, like I said, dy is an approximation, or delta y is an approximation of dy. Okay, now why would you use this? Well, why? Let's see. What if f of x at b is not easy to calculate? Right? What if that's without a calculator would not be very easy to come up with? That's a good reason to use this approximation method. All right, so let's talk about these questions here. What is the slope of a line in terms of dy dx? Well, the slope of that black line up there would be dy over dx. How do we write the slope of a line in terms of f of x? Well, that would be f prime of x. So if we set in the second part here the two representations equal, we can then solve for dy. So if dy dx is equivalent to f prime at x, right, or in our case up here, dy dx at x equals a would be equal to f prime at a, then dy should be equal to f prime at x times dx. So if we want to estimate the change in some function, so delta y for some delta x, then delta y can be approximated by the slope of the function at a point times the change in x that we would like to work with. Okay, so that may or may not be 100% clear yet, but we'll get to it here in a moment. So in summary, delta y represents the change in y along the curve, while dy represents the change in y along the tangent line. All right, let's look at a few examples. All right, example 1, pretty basic. We're just going to find dy using our differential form. So if I took the derivative of y with respect to x, I'd get dy dx. And if I took the derivative of x squared with respect to x, I would get dx. Therefore, dy in differential form, manipulating to find that, would be 2 times x times dx. Okay, still kind of skill-based. Let's get to an application here in the next example. Example 2, let y equals the square root of x. Find the differential dy. Well, dy dx, at this point, the derivative of square root of x should be your buddy. There it is. So dy, our approximate change in y from one x value to another, should equal 1 over 2 root x times the change in x. Okay, so evaluate dy and delta y if x equals 1 and dx equals delta x also equals 1. So what this is telling me is that, and I'm going to probably go over this sketch in just a moment. Actually, I know I will. But if I've got the square root of x, and I know when x equals 1, here is my f of a, which in this case square root of 1 is 1, and I want to approximate the square root of 2. And I want to approximate that value. Okay, so I'm going to approximate f of 2. And f of 2 I know is the square root of 2, but I want to approximate it using my tangent line. Right? My tangent line will yield me some value. And this value, when we talked about error, would be that far off, that purple space, right? So our approximation, which will be an approximation of f of 2, right? Approximation of f of 2 is going to be an overestimate. All right, so just so you know what we're attempting to do here. All right, so we're going to use dy, which is 1 over 2 root x times delta x. Now let's talk about where we get these values. Okay, so I'm going to try to use colors that make sense here. So at x equals 1, I'm going to plug in a 1 for x, and delta x is also equal to 1. So I'm going to plug in a 1 there. So dy is equal to 1/2. Okay, so that means that this length, let me see if I can highlight it on the graph with a color that's not already used. Okay, so if dy is equal to 1/2, that's going to be the distance here. Okay, so what that would mean is if I was trying to find an approximate value for f of 2, f of 2 would approximately be equal to f of 1, which was square root of 1 plus dy. And dy is in yellow here. So I'm going to approximate that the square root of 2 is 1 plus 1/2. So my estimate is that f of 2 is 3/2, or 1.5. Okay, so I've kind of done C in the process here. Let me see here how far off I actually am. So the square root of 2. So actual f of 2, right? Actual f of 2, using my calculator out to 3 decimals, is 1.414. Now within the context of my problem here, right, I could find the error. I could take my approximate, subtract my actual, and get that approximation. It's pretty good error. It's pretty small, but you can see how that would be an over approximation. All right, so part D, let's approximate 1.1, square root of 1.1, excuse me, using differentials. All right, so the first thing you should think is I'm working with the square root, right? I'm working with this function, square root of x. So I need to find dy. We just did, right? It was 1 over 2 root x dx. Okay, so if I want to approximate delta y, right? Of course, delta y will be approximately equal to dy. So if I were to draw a sketch yet again, here's my square root function. The nicest number to work with that's close to 1.1 is x equals 1. So your f of a value, right, will be 1. Now in this case, imagine, right, just imagine how close, and so this is not to scale, but let's put a 1.1 right here. So what would dx be? Dx would be 0.1. All right, so dx equal 0.1. All right, what's our x value? Well, x is equal to 1, right? That's our beginning of our interval, where we want to place our tangent line. I'm not going to use blue. Let's use a different color. How about green? All right, so of course, you know, you've got your approximated value for f of 1.1. And then we've got our actual. Find another color, purple. I don't know if I'm matching these to the last problem, but it is what it is. Okay, here's your actual value or output, which is the square root of 1.1. So I'm anticipating my estimate to again be an overestimate, right? And in this case, I'm going to use yellow. I know this isn't matching the last problem, but my error would be that little yellow space there. Okay, so again, one more time, let's approximate f of 1.1. Right? That will be f at 1 plus delta y. right? F of 1.1 would be exactly equal to f of 1 plus delta y, right? So here's the difference, right? When you're working with dy, you get an approximation. When you're working with delta y, you get an exact value. Laundry's done. Okay, so let's find dy. dy equals 1 over 2 root x. I know x is 1. dx is 0.1. And let's do a little work to find our approximation for dy, or our value for dy. dy is equal to be 1 over 2 times 1 over 10. So dy is equal to 1 over 20. So the square root of 1.1, or f of 1.1, is going to be approximately equal to 1 plus 1/20th. Okay, 1 plus 1/20th. So f of 1 was the square root of 1, which is 1 plus 1/20th. I'm going to approximate that the square root of 1.1 is, what would that be, 21/20ths, or 1.05. All right, let's use the calculator now. Actual, through use of the calculator, square root of 1.1 is equal to, hold on now, to 3 decimal places, 1.049. Now look at that, that's a pretty darn good approximation, right? Why was the approximation so much better? Well, because the change in x, the delta x, was much smaller. So the function and the tangent line start to diverge from each other, start to separate the longer or the wider the change in x is. So the smaller the change in x, the more accurate the tangent line, which makes sense, right? It's called local linearization. The more you zoom into a function, the more linear it looks. All right, we got one more example. Let's get to it. All right, example 3. The radius of a circular disc is given as 24 centimeters with a maximum error in measurement of 0.2 centimeters. So give or take, when this company is manufacturing discs, the maximum error on the measurement could be 0.2, meaning that discs could come out at 23.8 centimeters in radius, or 24.2. So we're going to use differentials to estimate how far off the area of the disc could potentially be. So let's tie area to radius with regards to a circle. So the area of a circle, oops, switched pen, there we go. The area of a circle is equal to pi r squared. Now, if I took the derivative with respect to r, just please notice this. This is going to be our r value, right? R equals 24. So like when we talked about the interval from a to b, this would be kind of like a. This would be the starting point, that spot where you want to work from. And a maximum error in measurement of 0.2 would be like dr, right? So you can imagine on a curve that if you had x equals 24, then your second value would be x equals 24.2, or x equals 23.8. Right? You'd have this curve, kind of like this. Right? You'd have a tangent line, and you could go either way with it. Right? Either way, we would have an underestimate, right? An underestimate of what the actual area would be. Right? This would be a of 24.2. This would be a of actual, a of 23.8, and then these would be approximations of said values. And an approximation of a of 24.2. All right, so we're going to use the tangent line in a moment. And how did I know that curve would look like that? Well, this is a quadratic, which opens upward with a leading coefficient of pi, right? So what I'm going to do is I'm going to find dA dr, right? Because where is dr coming from? Well, when we take the derivative, right, to find the slope of that tangent line, I'm going to get 2 pi r. So dA, remember dA is approximately equal to delta A. This is the change in area. Now, we think of it as change in area, but in the context of this problem, this is actually the error of area. Let's say that 10 times. This is the error of the area, right? Because it was intended for these disks to be 24 centimeters in radius. But instead, right, it could be up to 24.2 or down to 23.8. Right? So this is going to represent our error in area. So dA will be 2 pi r times dr. Now we know r and we know dr. So the change in area, given this error in its radius measure, would be 2 times pi times, what is r, 24 times dr, which is 0.2. Okay, so 2 times 24 is 48. So it would be 48 pi over 5. What does that come out to be? Is that 9.6 pi? 9.6 pi centimeters squared. Okay, so let's represent that on the graph. All right, here's perfection, right? This would be A of 24. But perfection is not achieved here. Our maximum error would be this, delta y. Now, I can't find that exactly without the use of a calculator, but I can find an approximation of that. And I'm going to approximate that by finding dA. dA would be this length here. And we found that length, right? We found that length and we found this length to be dA. And that would be the maximum possible error on the area of the disk. All right, guys, that's it for this lesson. We'll see you in the next video.